No, not here.
Fine expert.
Someone who can tell me what the difference or the similarities are between a channel, a stream, a flow, and a group.
Oh boy, semantics.
Not within the next couple of minutes, as we
Well, I understand, but believe me, I have been all over the web, and it's like a must be secret sauce.
Bob Mayer, there's an excellent U of I guy. How are you? Calling in from Montana?
Yes, I am.
There he is. Hello.
Oh, Rob Mayer.
So glad that you guys are making this available. Really looking forward to it.
And we've got Henry Cohen from New York. Is that the Henry Cohen?
Rob already has his affiliation on there. Gary's got his AAS Vancouver there. All right. We're bringing in folks from everywhere. David Carlstrom, he's local Detroit.
Oh, Vancouver.
Yes, to answer your question, that's Henry Cohen from New York.
And this is Jonathan here.
Oh,
Bill's
hey,
over-
Jonathan, how are you?
Oh, good.
Jonathan is my
Bill has
wingman
taken
here.
over Jonathan's studio. So if there are any technical issues, you can yell at Jonathan.
That's right. If it's content, I'll take the blame. But
If it's smoke and mirrors, it's my fault.
exactly. Yeah, definitions is like, I get into it in the presentation. What does ground mean? Depends on who you ask. Everybody will have a different definition.
That'll bring it right down to earth.
Yep. Well, at least I'm not all wound up in my work anymore. Don't own the transformer company anymore.
Vancouver.
Yeah, in fact,
think
that's
there
where
might
the
be a
owner
coffee mug
of
winner.
Jensen is there.
Is that going to be the coffee mug winner, David?
Yes, it's Vancouver.
I don't know, last couple weeks ago, we had Germany calling in at 1 in the morning. So we had a guy from Facebook Reality Labs, Sebastian, and one of his students from tuned in very, very late in Germany time. So
Wow.
we're going to start moving some of these meetings a little bit earlier in the day so that we can accommodate Europe a little bit more. As these things become more international, we want to try and pick up a few more time zones than just the US. So next
How
meeting,
wonderful is that?
it's totally cool. People are
It's-
really digging the whole section thing now.
It's just
And-
the democratization of knowledge.
Yeah,
It's
So it's-
cheaper than a plane ticket.
exactly. So it's 8 o'clock right now, and that segues very well into the benefits of AES membership. If you're not an AES member, the most useful thing, other than attending shows and all the other AES library and all that stuff, is getting the weekly loop that shows you what all the upcoming section meetings are for that week and for the upcoming weeks. And so you can plan out your watching your evening session attendance. So that's one of the huge benefits. But let me, I'm going to kick things off by doing a little bit of housekeeping here. So if I can get my screen shared in the right way. So there we go, share. All right, so here we are with our 27th. And as most of you know, Bill Whitlock, he's presenting his wide spanning knowledge, preaching the gospel of good signal interfaces. So we're looking forward to that. And my screen is not advancing. So the housekeeping stuff, just if you're looking for upcoming Detroit section meetings, next month in May, we have Ben Blau of Lawrence Tech University. He's starting up a new program there. So he'll be talking about gaming audio and introduction into the Lawrence Tech program. In June, Dewey Dew of Harman, ex-Knowles guy, he's going to be giving a talk on MEMS microphones in automotive applications. If you haven't been there already, you can find all of our contact info and recordings of our last meetings at aesdetroit.org. And so you should be able to find most of the stuff there, right, Kurt? I think you've been posting up the videos pretty regularly.
Yep, right. I'm actually looking for some other ways to host these virtual meetings too. Maybe I don't know, maybe we can talk about a YouTube channel dedicated to the section or something like
Right.
that.
Yep.
Okay.
Keep it simple, keep it straightforward. Yep, we'll talk about that a little bit during our upcoming meetings.
Okay.
Obviously, LinkedIn and Facebook, we have our, those are other great places. And then if you go to aesdetroit.org, you can also get on our email list. If you're in the election, if you're in the Detroit area, elections are coming up and we need some new energy in here. So usual appeal for volunteers, particularly in the committee area. If you're on the committee, you can drive who we want to see and hear. So reach out through the above contacts. So just for tonight, we are recording this and we will post it, just so you know. If you don't want to be recorded, don't say anything, shut your screen off or anything like that. As I mentioned at the head of the hour, if you can rename yourself to add some affiliation to your name, whether it's where you're from or what section you're in or what company you work for. You'll see a few folks have done that already. Post questions in the Q&A only. Is the Q&A showing or do we have chat? We might, put them in, I think the only chat is showing up. Q&A feature is not enabled. So put that in the chat. Kurt will take a snapshot of the attendee list. And then Bill, you're already a co-host. Kurt, you're a co-host. Kevin, I'm gonna make you a co-host so that you can take over as I have to bug out at about 8:30. One note is we have to wrap up at 9:45 because the West Coast has a meeting at 10 o'clock Eastern, 7 o'clock West Coast time. So with that, I'm going to, or you can stay on and do the West Coast meeting too. But we will have to officially give up our hosting duty. So with that, Bill, you can commence recording or presenting whenever you like and take it away.
Is this thing on? Isn't that the standard line?
We can hear you.
Good, good. Okay, we're trying to get our screens arranged here. Okay. Where is my pointer? There we go. Okay, and the advance is
You can just use, left now.
Oh, one other note, if everybody can mute, most people are muted, but just in case you aren't, please mute yourself.
I'll just use the keyboard.
Okay.
I just want to know where the pointer is. Okay, so that's the title slide, which challenged me for a little video processing, but it was worthwhile. And for those of you that don't know who I am, this is a bit about me. I've been in this biz since Quad 8 days back in the early 70s, but didn't really get seriously into interfaces and grounding until after Dean Jensen's death, and he left me Jensen Transformers. And I had used transformers before, knew that they were miraculous in the way they solve problems, but I had not a clue why. So for several years, I made it my business to dig as deep as I could dig into interfaces, especially balanced ones, and grounding, which unavoidably you get involved in grounding if you start looking for noise, because most of it comes from there. So that's a bit about me. Now I'm a consultant, doing a lot of fun stuff these days, but myth and misinformation is everywhere. We have, the unbalanced and audiophile people kind of annoy me the way they talk about exotic shields as if noise was something airborne like it was back in the 20s with tubes or something. These days, that's pretty rare, but we'll get into that later. And in all my years with Jensen, it put me to calling in technical support departments with a lot of manufacturers. And my experience has been that most of the people on their front lines of support are absolutely clueless about noise. There's a few exceptions, but they're pretty rare. People forget about physics and especially magnetics. It seems to be just completely overlooked. So they violate basic rules of physics. And one of my favorite little jokes is, you know, the cocktail party conversation. What do you do for a living? Oh, I design and install sound. They're like, what's so hard about that? You just plug the stuff together, right? Yeah. If you've worked in the biz, you know that's pretty far from the truth. So since AC power is the root of all evil, sort of, let's do a really quick review on how it's delivered and how it runs around in your sound system. So this is how power gets delivered to your house. This is a residential feed. And for those of you in Europe, things are going to be a little bit different. There's some pretty scary distribution schemes in use in Europe, in my opinion. But so you'll find out a little bit later that the only ground that makes any difference is the ground as it exists on the inside or your sound system side of that neutral ground bond. There is a neutral ground bond in the main breaker panel, or in the language of the code, the first disconnect panel after the service connection. And that has to be a meeting point of an earth ground, which is for lightning only. But primarily it's a bond of these two things, neutral and safety ground. And the bond is usually built into boxes. This, I think, is the interior of a sub panel that comes with the link disconnected. This would be the neutral bus, and this would be the earth ground or the grounded enclosures, part of the ground system that's distributed on the third wire. So physics will rule. This is one of my favorite slides. I saw this at Coilcraft, and they even had the courtesy to take their product name out of this guy's glasses. So the physics that I'm going to talk about mostly today, I'm going to assume most of you are familiar with Ohm's law and know about current flow and voltage drop and resistance, but I'll try to explain as I go. But Faraday's law, my hero, Michael Faraday, he was someone much like me. I don't care much for math. I don't get a very deep understanding of things by staring at a page of equations, but I'm a concept guy. And if I can visualize something, I've got a firm grip on it. And Michael Faraday was the same sort of guy. He was good at figuring out his observations. So basically we're saying here, or he said, that if current flows in a circuit, a complete loop, and in this case, we're going to make the current AC, we have a fluctuating magnetic field that will surround this conductor at all points. And if we represent these lines, or the density of lines as the strength of the field, with AC, you would see them growing in strength and collapsing to zero 60 times a second if this was AC power. And it would also change direction as the current flow reverses. So in AC, we have a field that goes through zero, grows in one direction, collapses, grows to another peak in the opposite direction. And an important thing to remember is that the field strength has nothing to do with voltage. It's all about current. It's amperes that convert themselves into magnetic field strength. Now, the converse side of all this is that if this fluctuating magnetic field, basically the rule goes that these lines of force, as they're called, if they cut a conductor as they expand and contract, it's that cutting that induces a voltage in this loop, not a current. I sometimes read explanations of transformers and want to strangle somebody because they interchange voltage and current. When voltage is induced, the current causes a current flow, which sets up a magnetic field. But when the field is intercepted, it's converted to a voltage. And if you get into the details of a transformer, as soon as current starts flowing in this loop, of course, it sets up its own magnetic field, which tends to buck the one that came in, So that's why the primary current on a transformer is related to the secondary current. I sometimes tell people, if you think the current in the primary induces a current in the secondary, that implies that if I had no load on the secondary of a transformer, the voltage would become infinite, which of course it doesn't. So just a bit of little pet peeve there. But in 2011, I wrote a paper about this. I had theorized, because I'd always wondered what drives the current in a ground loop, because loops clearly are what cause issues. Well, it turns out there's a voltage source in the loop, and that voltage source is hiding in the walls in the conduit. Because as current flows in a conductor, as we just said, a magnetic field is created. Here I've got a cross section of ROMEX, which has some other name in Europe, I'm sure, but basically a non-metallic sheathed cable that's held in relative geometry by the jacket. So in this case, imagine that the current is flowing out of the screen in one of these conductors, and by the right-hand rule, that would mean that the current is flowing clockwise around that conductor if the current is flowing out of the screen. But it will go through the load and come back and return on the neutral conductor, going in the other direction. So this magnetic field will be in a counterclockwise direction. Well, we know from our first experiences learning about magnetism that if we put two like-poled magnets next to each other, they repel. Like poles repel and opposite poles attract. So it distorts the magnetic field. They're actually trying to push away from each other, and there is a Lorentz force that at high currents can become extremely large. But it creates a space exactly, if the currents are exactly equal, which they will be in a normal circuit, the current that goes in one part of a load comes out the other side. So they're equal, but opposite magnetic fields. And there's a line right down here where there is zero field. So ROMEX actually does pretty good when it comes to inducing voltage in this ground conductor. And that's what the issue is. But if we go back and look at these wires, the way a commercial circuit, at least in the US, is normally wired, the ground conductor, there's one right there, green with a yellow stripe, has a total random positioning with respect to the two that may be carrying the heavy current in this circuit. So it may be much closer to the neutral conductor than it is to the line conductor, and no cancellation takes place. So we get, as pictured down here, a transformer symbol. It's basically a single turn transformer where the turn is whatever distance we want to consider, say between outlets. It's simple just to analyze a single instance of this happening. But if there's current flowing down one of these conductors and coming back on the other one, there are two magnetic fields. And they will, by transformer action, induce a voltage on this third conductor that's running in there, unless it happens to be positioned precisely in the middle. And even with ROMEX, we can't guarantee that. Even putting a twist and turn in ROMEX disturbs the position, because this is really a few thousandth of an inch of movement will upset everything. I first started doing tabletop experiments to prove this whole idea with a mic preamp connected to about 2 feet of wire, and then 2 other wires that I was pushing a 6 ampere current through from an audio generator and a load resistor, and played with the positioning to prove that this is exactly what's going on. So we potentially have a problem in the walls. And for existing installations, it's pretty much a case of we've got to live with it, because there isn't a lot we can do. But in new construction, there's truly a silver bullet. In fact, I've done a couple of consulting jobs where We have made the installation people's jaws drop because they do literally plug stuff together and there's no hums or buzzes. So there's the transformer that's in the conduit. This magnetic induction, of course, is strongly affected by geometry. It's highest with randomly positioned wires in conduit, which unfortunately the ways buildings are done. It's much lower with the uniform geometry holding the position. But most importantly, the voltage that's induced is directly proportional to the length of the wires that are next to each other, to how much current is flowing in those wires, and the rate of change in the current, because that affects the rate of change of the magnetic field, and the voltage induced in the secondary of a transformer or any coil is directly proportional to how fast the magnetic field changes. That's why spark coils in cars, for instance, kick out so much high voltage. It's because we build the field up and then all of a sudden we switch it off and it collapses very, very quickly and produces big voltages in anything in the magnetic circuit. So this DV or DIDT phenomena, the change in current over change in time, favors high frequencies. And we'll see in a minute, the plot is upward at 6 dB per octave. And there's a plot that I did. This was part of a paper that I presented at AES in 2011 called Ground Loops, the Rest of the Story, because we figured out where the voltage comes from. So I did a controlled experiment where I had conduit and I strategically placed conductors at specific distances apart. You can see it in the paper. And you can see here the difference between the same wires in the same positions and the same current with and without conduit. In this case, it was EMT, kind of a thin wall steel stuff. And you can see that it increased the coupling a bit at low frequencies, but then above 10 kilohertz, it kind of crossed over. And I think it's because of the permeability characteristics of the steel. It's a pretty low grade stuff. So it actually made it a little better, but it has no real significant effect. Now, the worst case comes from having the ground wire right next to either neutral or line, but having it close to one and as far away as it can get in a given conduit from the other. And predictably, that gives the highest voltages. So you can see here with a 6 amp RMS test current, this again was an audio power amp with a dummy load, had 6 amps of current over a 20-foot sample length. And we swept frequency. So this got into the noise floor down here, but you can see that we had about at 100 hertz or power frequencies, like second harmonic of AC power, about 10 millivolts over that 20-foot length. And it gets worse as frequency goes up. And by the time you get up into approaching 100 kilohertz, we're talking about several volts being induced in that wire over 20 feet. And I'll show you why light dimmers are such a nightmare in a second, because they spit out their garbage up in this region. So there are big ground voltages generated when there's a light dimmer current running anywhere in the same conduit. You can put your audio circuit on one pair and have another pair that's got a light dimmer on it, and they will couple strongly over that length. So it turns out the magic bullet here, you can see that ROMEX gets better, and type MC, this aluminum clad pre-twisted stuff, but it unfortunately includes the ground wire in the twist. And it turns out that it's better to let the ground wire run its own course and not twist it. But when you twist the two current carrying conductors, you are now putting them as close together as they can possibly be, which tends to cancel. Remember, if we could get these two conductors to occupy the same space, there'd be zero external magnetic field. The current flowing in one direction would create a magnetic field that would be completely canceled by the current flowing in the other direction. And that's one of the magic features of coaxial cable. it turns out that the center of each conductor is coincident. If you take the center of the outer braid on coax, it's physically on average in exactly the same position as the center conductor. And you can put current from and to through coax and try to detect an external field, and you won't find one. It's simply not there. And it also eliminates all the inductance in the circuit by the same token. So the magic bullet with wiring is to twist the two current carrying conductors together before you pull them into the conduit. Then it doesn't much matter where you put the ground conductor. That has the lowest induction of all. We only get up where we were getting 10 volts from a light dimmer, perhaps. We're down into a millivolt or two. It's a 60 dB improvement, at least 1,000 to 1, just from that simple act. And this has actually been tried. The first place that it was tried is the Bing Auditorium up at Stanford University. Turned out the electrical contractor had an engineer that had been to one of my lectures and kind of followed my work. And I told him about this crazy idea. And he found a vendor that would pre-twist the wire before they put the building together. And when they put the sound system in, it was just zero hassles with any kind of noise. So it's a good technique, and it's now been used a number of times by other people. So this is why a dimmer does such a bad job. This is an actual measured oscilloscope waveform here. I got a $10 Lutron dimmer at a Home Depot store, hooked it up with 500 watt incandescent bulbs and measured the current. So this is 8 amperes peak into these bulbs. But if you expand this center area, and of course you can see, I assume you know how dimmers work, but I'll explain briefly. A dimmer works by waiting to turn on the semiconductor device in it, either a triac or a silicon controlled rectifier, until the voltage reaches a certain point, and then it triggers this latching on device, the triac, and it'll remain conducting for the remainder of the cycle as long as current's flowing through it. And then it turns itself off, and then it waits for another trigger in the negative direction. So as you move the dimmer control, this trigger point moves back and forth in phase. As you pick a low trigger voltage, it'll turn on for 90+% of the cycle, and the light's at full brightness. And here, predictably, the worst case is about half brightness. You wait until the sine wave is right at its peak, and then you turn it on. And when it turns on very, very quickly, mostly to save its own life, because the dissipation, if it's halfway on, is very high, and it would get hot and burn itself up. But if it switches cleanly from off to on, it'll only get warm. So if you look here at 5 microseconds per division, this current rises from 0 up to nearly 8 amps in just a few microseconds. And if you do the math, you can convert a rise time into an equivalent bandwidth. And this rise time indicates that there are very strong harmonics up to 70 kilohertz, which was the upper limit over here. We ran this up to 50, which was about as high as I could push my power amplifier to get a lot of power out of it. So that's why light dimmers are notorious for causing hum and buzz problems. It's not the conduction or shared conductors that most people think. It's the magnetic fields is what kills you. And anything that draws current intermittently will do the same thing. Things like fluorescent lights that turn completely off and re-trigger every cycle. Switching power supplies, anything that arcs has a lot of high frequency, fast moving current changes. And sometimes a steady like white noise will come into the building from corona discharge happening on insulators if they get damp. And of course, if you look high enough in frequency, you'll see that power lines make excellent AM antennas, and you'll see a lot of that. So AC power in the grounding system is wired the way it is because it's required by code. And you can't violate code unless you want to get in a lot of trouble. And it has all of this built in. So that's not an option. So an unfortunate fact of life in sound systems or any system is that small voltage differences will exist between the ground connections and outlets caused by that transformer that's built into the wiring in between them. And even if we can get away with not using the ground connection, we'll have a little section here that explains two-prong equipment. And I'm sure you've probably seen a lot of it. Well, the manufacturer has to go through a lot of hoops in order to dispense with a ground connection as safe for safety's purposes. So even if the equipment has no ground connection, there are things called leakage currents that can cause problems. So let's talk about ground for a minute. Of course, anybody in Europe or really elsewhere in the world is going to know ground as earth. And to a utility power engineer, that's literally what it means, a connection to soil, because their primary concern about grounds is lightning strikes. And lightning is one source of current that actually wants to return to Mother Earth. But in electronics, we come to use the term ground, meaning just a return path, usually to the one end of a battery or a power supply, something that is not actually connected to Earth. So there's a lot of confusion created by the two different meanings. And of course, my favorite definition of ground is that it's a fantasy invented by engineers to make life simple. Because if you drop those little ground symbols on diagrams, you can assume, and it'll sometimes bite you, but you can assume that they're all at exactly the same voltage and you don't have anything to worry about. But in the real world, conductors have resistance. And anytime current flows through a circuit board trace, a wire, even a chassis, a small voltage drop results. And you'll see in a minute, we're dealing with some very small quantities here when we start talking about system noise. So the sad truth is that grounds circuits usually serve more than one purpose. And in our case, one is for safety, and the other is as a reference point for signals, very often in a system. So the meaning of ground has gotten very weird. In fact, there's a lot of magical thinking around ground. Some people think that these ground voltage differences can be shorted out. And I don't know how many recording studios I've seen with enough copper to support a copper mine, massive bus bars and everything else trying to short it all out rather than trying to figure out where it's coming from, analyze the current flow. Or people that spend hours or days experimentally moving wires around, just listening, it's a process that usually ends when somebody says, I can live with that, and they put an end to the misery. Or people think that Neil Munsey used to call this the sump theory of grounding, that you can somehow skillfully route noise through a wire to an earth ground connection, and the system will suddenly become quiet because the noise will flow into that earth connection and disappear forever. Well, that's counter to any electrical theory. What goes in has to come out. So think about an electronic system in an airplane, sound system on an airplane. And they get buzzes and hums, but they're usually at 400 hertz instead of 60, because that's most of the power on a plane is high frequency to save on weight. But they don't drag a ground wire. It doesn't make the system any quieter to have it, quote, grounded. So that there's something just godlike about the absolute zero voltage reference of a stake in the ground is just lunacy. Absolutely not true. In fact, if you think about the towers that carry utility electricity around, all of those are grounded. And in a lot of places, the neutral is actually tied to an earth ground stake. If you look around your neighborhood, if you have above ground utility wiring, about every third or fourth pole, you're going to see a ground wire running down the side of that wooden pole. And that's to give a convenient place for lightning. If it should hit that elevated power line, it can find a pole not too far away to go to ground and avoid that impulse flowing through the whole system. But it also means that the voltage drop on the neutral conductor as this goes through your neighborhood is now superimposed on all these ground stakes. So if you drive a stake in the ground, you have no idea where you are in this network of voltage dividers that's created by the utility company. And that's not to mention all the electrical connections that plumbing pipes make. And then I have some stories, if we have time, I can tell about that. No code violations, but I once found 13 amperes flowing on a cold water pipe coming into a building. And there was nobody had done anything wrong. But this pipe ended up going under a rehearsal hall stage, and nobody could play an electric guitar on that end of the stage that was anywhere near that water pipe. So the other misconception is that wires make the voltage on both ends equal. Well, they don't, because they have resistance. And even if we had room temperature superconductors and the resistance went away, we'd still have inductance to deal with, which won't go away unless we can figure out a way to make the magnetic field and Faraday's law disappear. And this annoys me a lot of times when I hear people, especially power conditioner people, that think they've got the magic bullet for power line noise, talk about noise. They talk about it as if it travels around or exists only on one wire. And I remind them that every voltmeter has two probes. Every voltage I measure here is with respect to some other place. All voltages are differential or relative. So when you talk about a voltage, you have to talk about referred to what. And that's my favorite way to stop one of those mindless conversations about noise traveling around on a ground wire or something. With respect to what are you going to use as your golden reference point? As we said, earth ground is all about lightning, pure and simple. Now, the power company will also have events where lines fall as a result of a car crash or something, and they'll fall into each other. And this can temporarily create some large currents flowing through soil. So they do look at it as a fault current, absolute safety net. There's lots of studies about if you were standing on soil in your bare feet and your feet are 3 feet apart, what kind of a voltage gradient could you live through if you had, your bare feet in contact with the soil? And it's pretty amazing. You get up to like 3,000 volts per meter in the soil. And if it doesn't last too long, a human being can actually survive that kind of current through their legs. Kind of gruesome to think about, but the main reason we have the safety ground or the third prong is to protect us from equipment failure. And it doesn't take a PhD to figure out that if something goes wrong inside a piece of equipment, like a shorted power transformer or a pinched wire, that very easily 120 volts could come in contact with the chassis or some other conductive part, even if it's a wooden cabinet. Eventually, signal connectors are tied to ground and safety ground. If there's a safety ground on there, then there's an alternate path. But insulation failures prevent touchable parts of a piece of equipment from becoming an electrocution hazard. And they're also intended to remove power from the circuit quickly through something called a fault. Because if a short circuit occurs and there is a third connection on the equipment, like the famous electric drill, the metal case, and it shorts out, and guys standing in water or got one hand on the plumbing or something, the case of the drill becomes 120 volt charged and he gets electrocuted because it puts a current right between his two arms, right through his chest cavity, and death. But if it's a lesser current, I left out the little gruesome section about biological effects of current, but at about 10 milliamps from arm to arm, it's enough to paralyze your breathing. And a lot of people with shocks that don't kill them die after several minutes because they can't breathe. And, you know, they suffer a death the slow way. But at higher currents, it'll directly cause 100 milliamps or so fibrillation of the heart, and it's a quicker death. But at even higher currents, it'll generally cause burns. But anyway, if the green wire is in place, then the current doesn't go through anybody's body. It flows through the green wire back to the neutral connection at the breaker panel. So it's an alternate pathway for the current on the live conductor to get back to the grounded conductor, the white wire or the neutral. And if this connection is low enough impedance, the fault current gets very high. And a typical fault current runs from 150 to 1,000 amperes. And it largely depends on how much wire is between the breaker panel and the outlet. On 100-foot runs, it'll be closer to 150 amps. But if you get one that's only a foot or two away from the breaker panel, it could easily hit 1,000 amps. You throw a short across your incoming electric service, and you're likely to see several thousand amps before anything happens. So this happens independent of any earth connection. And here it is in a diagram. So we have the transformer on the pole out in your backyard, goes into one of the buses in your breaker panel. I haven't shown the other side here just to keep this simple. But neutral, the normal return path, normally the current would flow like this, neutral through the equipment and back. So we have a complete circuit. And the ground doesn't get involved, of course, there. But if there's a fault in the equipment, now we have current flowing from the hot side of the power line to the chassis and the ground connection. And this carries it back as an alternate path. And the current in this loop is now high enough to kick the breaker out. And at 150 amps, believe it or not, it can take several seconds for that breaker to react. Only at 1,000 amperes will it kick out in less than a cycle of the AC. But fuses and circuit breakers are slow generally to tolerate startup for motors like refrigerators and air conditioners, but it also makes them slow to respond to faults. But it's enough to protect the wiring, and that's the intent. The wire doesn't get hot enough to start a fire. Now, I actually sat in on a seminar once at a trade show, CDS show for all the high-end home theater stuff, where some guy was actually telling the audience that if you wanted to lower the noise in your sound system, what you needed to do was disconnect that noisy green wire from the outlet for your sound system and instead drive your own ground rod just outside the room and tie your equipment to that. Well, I got up and started waving my hands at this moron and tried to get him to stop. And eventually I got him disbanded from the show. But if you look at what happens in a case like that, this stays electrified depending on just how much resistance is in the soil. And it can be very considerable. Code allows each of these ground connections to have 25 ohms of resistance to the surrounding soil. That's even for an 8-foot deep ground rod. And in some soil, you just can't get there. It's just too dry. So anyway, that would only cause a couple of amperes to flow if there were 25 ohm connections here. And that's not going to trip the breaker. So the chassis here would stay at some very elevated and dangerous voltage. And the only other thing that would happen is the worms would all crawl out of the ground because they hate electric current flow in the soil. So if you fish a lot, there's a good way to get worms. So we have this safety ground wire that has to be there and a lot of equipment that has to have it in place to be safe, simply because the manufacturer doesn't want to spend all the money to double insulate everything in his power supply. It's generally very uneconomical. It's much less expensive to put a safety ground connection on. So if we have two pieces of connected equipment plugged into outlets that are physically fairly distant, like 20 feet, this voltage that gets magnetically induced in the safety ground wire is now going to be applied through the ground connections to the ends of our signal cable. And this will have some devastating effects depending on what the interface, what type of interface it is. If it's unbalanced, it can be a real disaster. If it's a balanced interface, you've got a fighting chance. So I'm going to call ground voltage differences GVDs. But the bottom line here is that a properly installed, fully compliant AC power wiring normally creates these small voltage differences. Now, if you ever see a voltage over 3 volts, I won't explain why that is, but it's the maximum voltage you should ever see between ground and neutral at an outlet. And it has to do with voltage drops under full load. They're allowed to be 3 volts on each trip back to the ground on the panel under full load. That's a recommendation by code. So the total voltage drop would be 6 volts, which is 5% regulation at a 120 volt outlet, or would cause a 5% drop in voltage. So half of that would appear between neutral and the ground. So that's why it's the maximum. Now, I'm sure everybody knows what noise is, but it's worth mentioning. It's any undesired signal. It can be hiss, it can be hum, buzz. Most usually it's the hum and buzz that are the problem. A certain amount of hiss is entirely normal. And there are other designed-in problems that we'll mention as we escape here. But the signal interfaces are generally the danger zone. So the victim is the signal interface. Now, an interface consists of a device's output, the line driver, the interconnecting cable or line, and the device input. And this little subsystem is responsible for moving signal from one box to another, hopefully undistorted, good frequency response, and no added noise. It takes 2 conductors in every case to do that, because electricity only flows in a complete circuit. So you have to have a to and a from. And if you disconnect one of those, it'll find another pathway, and it's usually pretty bad. So there are 2 kinds of interface for signals. There's balanced ones, which use the same 2 wires that an unbalanced one does, but in an unbalanced interface, we ground one of the conductors. But the important point I want to make here is that the status or definition of an interface depends only on the impedances with respect to ground of those 2 conductors. If we have a 0 ohm impedance on one of them, the grounded one, that automatically makes it unbalanced, because the other line is going to have some higher impedance, the one that has a signal, anywhere from 50 to a few thousand ohms. For a balanced interface, we try our best to make the impedances of those 2 wires with respect to ground equal. But remember that since the driver, line, and receiver are connected in parallel, it means that all 3 of these items have to remain balanced: the line, the driver, and the receiver. If you ground it anywhere along the way, it automatically becomes unbalanced and loses its magic properties. So schematically, here is a balanced and an unbalanced interface. Pretty straightforward. Now, I think it's just ironic that unbalanced interfaces have survived so long. It's primarily a testament to how cheap they are, but they are inherently susceptible to noise coupling, and I'll show you why. But, you know, $20,000 equipment is covered in RCA connectors. It's just weird. So the reason that unbalanced interfaces are so bad is caused by the resistance of that grounded conductor from one end to the other. It has nothing to do with exotic materials or shielding. You can use zip cord. In a lot of cases, you'll improve the noise of an unbalanced interface simply by using heavier gauge wire on the ground side. And you'll find through experimenting that it has almost nothing to do with shielding. Neil Munsey used to do some experiments with mic cable and replacing it with zip cord and taking off the shield, and made no difference unless you put it under some extreme stress. So shielding is not what it's about. It's about the resistance of this. Now, even if I don't have a ground connection on these two pieces of gear, there is another small current that will always flow. Two-prong plugs have to have UL. The UL limits these very, very heavily about insulation, creepage differences, over temperature protection, mechanical abuse. They control spacing, so you can bend things and still not have shorts. So they have leakage currents. And these leakage currents are intentionally low. If you've ever touched, say in your bare feet on a concrete floor, a piece of equipment that with a two-prong plug, you probably felt a little tickle. Well, what you're feeling is some tiny fraction of a milliamp flowing through your body. It's just enough to cause a sensation, a little tingling. Now, if you ever disconnect the safety ground on something with three prongs, be careful, because 3.5 milliamps hurts. It's not enough to kill you or paralyze a muscle, but you'll want to let go of it right away. And there's some three-prong equipment that actually has leakage current as high as 5 milliamps, but UL requires that it have a warning label about high leakage. But this leakage comes about because there are capacitances inside these pieces of two-prong equipment. They're either parasitics, unintended, like between the primary and secondary of a power transformer, or even a wall wart if it has an external supply, or it's part of an RF filter if there's digital stuff going on in the box to keep the high frequencies from getting back out and onto the power line and failing an FCC test for radiation. So they put capacitors there to try to attenuate the high frequencies. So even if I have a system where nothing is grounded, I can still have noise problems due to these tiny currents flowing in the shield. And AC power is not clean. And remember, these coupling mechanisms, these capacitors favor high frequencies because the apparent resistance of a capacitor drops with frequency. The higher the frequency, the more it looks like a short circuit. And the lower the frequency, the more it looks open. So we have lots of stuff. This is a spectrogram that I ran years ago on an actual AC outlet at Jensen Transformer's office. And of course, you see the big line at 60 hertz. And now we see third harmonic, fifth harmonic, seventh harmonic, ninth harmonic. You'll see a harmonic series due to the distortion of the AC waveform. And this particular signature, odd order harmonics, is due to the flat topping of the sine waves, and which is largely caused by electronic power supplies that draw current only at the tips and the peaks of the AC power. So it tends to flatten the waveform on the grid that way, and it shows up as harmonics. So this would show up as somewhere around 2 or 3 or 4% harmonic distortion. But be very, very careful connecting to the power line. This was done with an isolation transformer. But there's lots of stuff from switching power supplies, all this high frequency stuff, 10 kilohertz or so. And then when you get out here, this is the bottom of the AM broadcast band, and you can actually see local AM radio stations coming in on the power line. So there's pretty good transmission up to fairly high frequencies. So here's an example of how you can have an objectionable noise with no grounds in the system. Let's say we have nothing but an integrated amplifier and a CD player, and they're connected by a 25-foot audio cable. And it's got a 26 gauge drain wire and some foil shielding. And we find that its end-to-end shield resistance is 1 ohm. And we measure the leakage current that's flowing between those two ungrounded devices. And you'll see I chose this number for a reason, but we have 316 microamps flowing through the shield. And this is about half the UL limit. So from Ohm's law, let's calculate the voltage drop along the length of the shield. It's 316 microamps times 1 ohm. So the end-to-end voltage for the shield is 316 microvolts. Well, consumer reference level happens to be minus 10 dBV, which is 316 millivolts. So we now have a 1,000-to-1 ratio between noise and a reference level signal, which makes our signal to noise ratio 60 dB. But the dynamic range of the system is now, and this is 20 dB worse than a CD player. That's if you include 15 dB of headroom. And that may confuse people, but if a CD has a dynamic range of 95 dB, the upper 15 dB is headroom for signal that goes above the reference level before it clips. So when we say signal to noise, we're not talking about a maximum signal, we're talking about a nominal signal that's 20 dB down. So anyways, 80 dB plus the 15 dB of headroom gets you 95 dB. So this would have to be 80 in order to preserve the dynamic range of a CD. But if I replace this 1 ohm resistance cable with one that has a lot less, Belden makes a beautiful video cable. It has a lot of copper braid in its shield, and its end-to-end resistance is only 0.065 ohms. That alone will add 24 dB to the signal to noise ratio. That would bring it down to 84 dB. So it's about resistance, not the shielding effect of the copper. It's about the resistance of the copper in the shield. Now, if I had that same system and I grounded both ends, now the few millivolts that might be induced in here is much, much bigger. It would be 10 or 20 times bigger than the 316 microvolts I had without a ground connection. And that's why people are so prone to put a lifter and interrupt these ground connections. They get one of those 3 to 2 prong adapters. DJs are famous for this, and so are home hi-fi enthusiasts, because it's the cheap and dirty way to make a noise go away. But unfortunately, it also turns your system into an electrocution hazard. If something should go wrong, remember that 120 volts will travel through these signal cables. So one piece of failed equipment with a lifted ground can cause either the entire system to become electrified at 120, or if this ground connection is really here and this one's interrupted and something goes wrong here, enough current will flow here to burn the cable. Tens of amperes flowing through an RCA cable is not a good thing, and it's probably going to catch on fire. So it goes from bad to worse. Unbalanced interfaces are just really not suitable for big systems. Now, how much noise is too much? Well, a little review. Our ears perceive 10 dB reductions as about half as loud, and 2 or 3 dB just noticeable. So making a 10 dB change in the signal to noise ratio is noticeable. But surprisingly, I was surprised when I read this paper years ago. Louis Fielder of Dolby Labs wrote a paper in 1980 showing that because of the properties of the ear, our ears are such wonderful filters, especially for what's called stationary noise, because it has on a spectrum analyzer, it stays stationary, like 60 hertz in its harmonics. The buzz is stationary. Our ear is incredibly good at picking out that kind of noise, even if the levels are buried below the random noise. And I found out the hard way when I worked at Capitol once too, that crosstalk can be measurably buried in the noise, but your ear will hear it as a little coming from an adjacent track, even though you can't measure it. So he wrote a paper that showed that up to 120 dB of dynamic range may be needed in a home theater or a critical listening environment to, as they say, suspend the disbelief that you're listening to recorded music and not real. But anyway, when I talk about noise in a system, it's this kind of stationary buzz and hum that I'm talking about. Usually hiss is a gain structure problem. We won't go into that. Now we have the balanced interface. And anybody who's ever been to one of my lectures knows that this is my cause celeb. I get really mad at definitions like this of a balanced interface. The conductors are equal in voltage and opposite in polarity to the other. And the circuit that receives the signal is called a diff amp. And this opposing polarity of the conductors is essential. Wrong, 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 wrong. Everything about that definition is dead wrong. It doesn't even mention impedance, which is the single defining property of a balanced interface. Symmetry of signal voltage swings is irrelevant to noise rejection. And we had the same problem when we proposed the common mode test for IEC. A whole bunch of people got upset that we were, not talking about equal and opposite voltage swings. Here's a couple of correct definitions by people that know a thing or two about balanced interfaces. One is Henry Ott, who's a distinguished member of the technical staff at AT&T. Essentially, the telephone company invented balanced interfaces because they were up against some huge problems trying to haul voice signals across miles of telephone lines in open air, very often running next to power lines. So they had a serious noise potential. But a balanced circuit is a two-conductor circuit. That third pin is not required. Ground is not part of the circuit for a balanced interface, where both conductors and everything connected to them, as we mentioned earlier, have the same impedance with respect to ground and to all other conductors. The purpose of balancing is to make the noise pickup equal in the two conductors, in which case, if the same signal is on the two wires, it can be rejected by a receiver that's designed to reject common mode, or a signal that's the same on both wires. And this is the informative annex that, with the help of John Woodgate, we wrote for the IEC to kind of counter the arguments before they started. Only the common mode impedance balance of the driver, line, and receiver play a role. The noise and interference rejection property is independent of even the presence of a signal. And I often argue with people and say, how do you test a system for noise anyway? Don't you remove the signal and crank up the gain and listen? Well, if the signal had anything to do with rejecting noise, why would we take it away if we're going to measure the noise? So anyway, it's an argument that makes no sense. The signal can exist entirely on one line as a greater on one than the other. They can be completely equal, which is nice. It has a couple of other advantages. Symmetry, which is what this is called, concerns headroom. In other words, when you have limited supply voltages in your driver, if you can get both a plus and a minus output to have symmetrical signals and clip at the same time, you'll get 6 dB more signal. And it also has to do with capacitive crosstalk between unshielded pairs. But it has nothing to do with ground noise rejection, which is 99% of the reason we use a balanced interface in the first place. So schematically, here's what a balanced interface looks like. So we have two impedances associated with the driver and two more important ones associated with the receiver. And these are called common mode impedances. And here we're using the letter Z to mean impedance. So we have a differential mode signal, which is the voltage on one line with respect to the other. And then we have common mode voltages, which appear because of the ground noise. If I stand over here as my reference point at the receiver, and I look at these two lines, they are both going to have a voltage that is added to it by the voltage exists here with respect to here, but through the ground, it makes connection to the driver and puts that noise on both of the send wires. So when this comes back, I've got my differential signal, but I also have this ground noise superimposed on both lines. Well, if I have a good differential amplifier, I can ignore the voltage that's the same and only amplify the voltage that's different between these two. And this is called a differential or balanced receiver. So the ideal receiver would respond only to that differential and not have any response at all to common mode. But in the real world, we can't avoid some of the common mode signal leaking through, even with a transformer. Some of it's going to get through, but it'll be very, very tiny. So common mode rejection, or CMRR, is the term that's abbreviated. And I take this so seriously, it's on my license plate, which also started some conversation with DMV about what does that mean. But it's a ratio. It's not a signal level. I often see it in print. Somebody says CMRR is minus 90 dBu. It is not a level of voltage. It's a ratio. It's just plain dB. And it's a positive number, not a negative one, because it's the ratio of signal to common mode. So it's a positive, big positive number, hopefully. If you turn a balanced interface on its side, and this is when the light comes on for a lot of people, it becomes a Wheatstone bridge. This is the driver impedances. These are the receiver impedances. The bridge has some very interesting properties. The goal is to make the ratios of these two pairs exactly the same. And I mean exactly within 1 part in a million. Well, it turns out that all of these components will have tolerances. We all know how hard it is to make precision resistors. And it also turns out that the worst possible case for unbalancing the bridge with tolerances is when they're all equal. If these were all 10K, I could move one of these by 0.01% and unbalance the bridge. But if these were 50 ohms and these were 50 million ohms each, any of these resistors could be off in value and the bridge would hardly get unbalanced at all. And that's the secret of a transformer, is that these resistances are huge. And these are the normal source impedances for devices. You doing okay on time? I've been keeping track. So this has given rise to marketing wars, basically. Everybody's trying to get these big numbers. And this all started when people who did not understand how this bridge works started measuring common mode rejection by simply shorting the two inputs of a receiver together. Say, okay, I'm driving them with the same voltage. Yeah, but the source impedance makes a huge difference. It can't be zero. There's no equipment out there with zero source impedance. So in real world equipment, the driver output impedances, these two, are not zero. They're actually set by some typically 5% resistors, but even if they're 1%, it's just a little better. And sometimes electrolytic capacitors that have terrible tolerance. The real problem is real world receivers. Electronically balanced receivers, basically little diff amps, 4 precision resistors in a package with an op amp, laser trim to 0.001%, makes no difference. Once you connect these super precision resistors in series with these that aren't, the bridge gets unbalanced just because of these. The only thing that saves it is to make these incredibly high. And once I realized that, which happened back around 92 or 93 after I'd owned Jensen for a few years, I had the aha moment one Saturday morning standing in the shower. I know how to make an electronic circuit imitate that property of a transformer. It's all about common mode impedances. So I came up with a circuit. I don't think I even show you here, but it's made by that corporation. It's called Ingenious. And I patented that in 1996 and licensed that corp to make it. It's the first IC that actually imitates a transformer. In fact, it'll outperform the best Jensen input transformer. And some people think that was really stupid for somebody that owns a transformer company, but hey, it's progress. Pardon? Well, yeah. The transformer can outdo it a little bit at very low frequencies, but at high frequencies, the Ingenious chip actually wins. But to show you how bad most of these ordinary diff amps are, the SSM 2141 or one of its incarnations, it's an op amp on 4 precision trimmed resistors. If you check it with shorted inputs or a precision driver, it'll have its advertised 90 dB of common mode rejection. But if you put 1 ohm of imbalance at the driver, it'll drop to 65. So it plummets in a real world application. The only way to get 90 dB from it is to put it on a test bench with test equipment. It won't do it in the real world. So transformers ignore things like that. You can take a Jensen 11P1, which is a standard line input transformer. If you connect it to a 600 ohm imbalanced source or even a totally unbalanced output, its common mode rejection at 60 Hertz will only drop from 107 dB to 100. It's extremely tolerant of sources. And that's the magic. Everybody took them for granted over the years. They just worked. So if you work out the numbers in a circuit simulator, this is what ends up happening. If you look at imbalance, and this is a real world range of normal imbalances in balanced signal sources. The balanced output on a piece of gear is going to be somewhere in this region. And completely unbalanced sources will be over here, 100 ohms to up to 2000. Actually, IEC regulations allow output impedances on consumer gear to be as high as 2K. So if you have typical diff amp input impedances in the 5K to 50K range, you can see the common mode that you will get. It'll range from 50 dB to down here at the other extreme, it could get as high as 100 if you had a really tight signal source and a receiver that was on the high end of normal. Most of them fall somewhere here in the middle, and the IEC test actually uses 10 ohms as the imbalance for testing. So it'll show that perfect one as something around 60 or 65 dB, even if it's trimmed to be incredible with a short circuit. But it also shows that if you raise the impedances up to 50 megohms with a transformer, even with an unbalanced source, say find 600 ohms over here, you're going to get 100 dB or so, like we showed on the previous slide, and it won't degrade much. But Ingenious is very close to that because it's at 10 megs. So it gets pretty close. And in fact, some of the Ingenious chips get even higher than that. But anyway, it's a huge improvement over a standard diff amp. And don't worry, I'm not making any money on it anymore. Patent became public a few years back. So back in 2000, or in 1999, the IEC recognized that their test for common mode didn't have any correlation to real world experience. And they asked for comments. And I felt like the kid in the back of the room waving my hand and said, I know what's wrong, I know what's wrong. And I proposed a new test. Well, it was eventually, after a little arguing, adopted and published in August of 2000. So it's now part of the common mode test listed under amplifiers. And to my delight, Audio Precision actually incorporated this test with a single push button into several of their analyzers. Here's one. So you can do an honest to goodness, meaningful common mode rejection test. And basically, this is the test procedure. The normal reading is done in a conventional way. Differential in, you measure this, you call it 0 dB, it's your reference point. Now, the old method actually had a clever way to make this source perfect. So it had zero imbalance. You'd trim on these things and keep flipping the switch until you got the same meter reading. And they took that as, quote, the common mode figure. Well, that had nothing to do with a real world application. So in the new test, we put a 10 ohm imbalance first in one leg, and to keep them from trimming the chip to compensate for this one, say, okay, now put it in the other leg. So you've actually got to do a good job and look for plus or minus 10 ohm imbalances out in the real world. So this test actually has some correlation. And if you know anything about SynodCon, Pat Brown has also incorporated this into his amplifier standard tests, which is another good thing that's underway to keep manufacturers honest. How much common mode is enough? Well, this gets into some math, and I'm not going to spend a lot of time on it now because it, again, deals with headroom and dynamic range. But it basically depends on how hostile your electrical environment is. The signal to noise ratio will actually be equivalent to the common mode rejection ratio if you're in a fairly hostile environment where you might see 1.23 volts of ground voltage difference, or +4, basically. But if you're in a less hostile environment where you may have only 120 some millivolts of ground voltage difference, then you could use 20 dB less common mode and get away with it. Now, Neil Muncy and several colleagues have agreed over the years that 80 dB of real world common mode is generally enough to keep a system quiet, but the 50 dB just won't cut it in all but the quietest of environments. Neil also popularized the pin 1 problem.
Chime in with a quick time check here. It is 9:15, so we've gone 10 or 15 minutes over. We don't have to stop immediately, but
okay, let me zip through the rest here and then we'll get to questions.
Yeah, cool. Thanks.
All right, thank you. So the pin 1 problem is pretty straightforward. This is how it works. It's what happens when you land pin 1 of an XL connector on signal circuitry, like a circuit board in a part, instead of landing it to the chassis, and this is what AES 48 is all about. You land pin 1 directly on the chassis. It's supposed to be an RF shield extension so that the cable shield becomes part of the box and you leave the signal circuitry alone. Otherwise, when some of the ground currents start flowing in the shield connection up here, the voltage drops in the traces on the board will make the output have a hum. And that's called the pin 1 problem. Magnetic fields and coupling. Twisting is what saves us from magnetic fields. Because if we took the wires here and twisted these together, there would be no pickup loop area, and it could be next to a magnetic field and not pick up anything. So twisting is a way to keep the two conductors in a balanced interface, basically in the same physical position, by putting one first closer to a source and further, further, works by averaging their positions. For the same reason, we shouldn't worry too much about the magnetic field around power cords. They get a bad rap for being sources of strong fields. If you do the math, magnetic fields fall off as the square of the distance around them. So as you get further and further from this cord, the two fields blend together and cancel each other. You can only see them individually if you get really close to the two conductors. So by the time you get to 10 times the distance of the spacing, for a typical power cord is about 2/10 of an inch. If you get 2 inches away, there's almost no field left. It's 1% of what it would be up here. So don't be too paranoid about power cords. Another interesting property of cables, especially coaxial cables, is that below about 4 kilohertz, the noise problems are caused by the resistance of the shield, as we explained before. But as the frequency goes up, the inductance of this straight wire formed by the shield dominates its impedance. And that transformer couples to the center conductor. So at frequencies above about 40 kilohertz, the noise from end to end on this cable is subtracted out of it by this action by the time it gets to the other end. They make their own noise disappear at high frequencies. Now tie this in with the claims made for power line filters. Their filters only begin to operate typically around 40 kilohertz. And by that time, the cables themselves, if they're coaxial, are dealing with the noise. So it makes these filters kind of a, who cares? Transmission lines that you can see in the slides here, it has to do with characteristic impedance. And then there's consumer cables and the snake oil. So one of the things I love to say is exotic cables, even if they're double or triple shielded and made of pure unobtainium and hand woven by virgins, won't have any significant effect on hum. But if you put lots of copper in the shield, it's a surefire way to get rid of hum. So this talks about balanced power and power conditioners. Basically, most of the benefits from a power conditioner are actually due to the tight clustering of output outlets. That means that ground voltage difference is nearly zero for two outlets that are physically right next to each other. Unbalanced conversion. This is something we're talking about in the standards committee, so I want to go through this a little bit. This defines the levels. There's a 12 dB difference in consumer and pro. Rain seems to think you can use a transformer to do this, but you can't. It's physically impossible. The actual gain's only 3 or 8 dB, most. You can wire a cable correctly and do a much better job. And I hiss and boo every time I go by the booth of a company that makes these, because these are exactly the wrong way to make an interface between an unbalanced output, say a CD player, into your console. Do it this way. It's a huge difference between using 2 conductors up here and 3, because now the chassis current, the noise, has a separate place to flow down here. Up here, it has no choice but to flow through the same conductor that's part of the signal circuit. So this noise gets added directly to what's delivered over here. And here you'll get at least 30 dB less. Now, going the other way, this is bad. This is a dilemma, because there's 3 basic different types of output stages. There's the voltage-driven outputs, which are very, very common. There's the newer electronically balanced outputs, where theoretically you can ground one of the outputs without hurting anything. And there's a true transformer output. Now with these, here you can't ground one of these outputs, or you're going to overheat and possibly damage one of the drivers. It'll see a short. Over here, you should ground one of the outputs because the common mode impedances are high and undependable. And down here, you must ground one of these, or you'll get simply capacitively coupled tinkly sounds coming through the transformer. And the manufacturer probably won't tell you. You're going to experiment and be frustrated. And, it's terrible. And it's one of the issues we're dealing with in the standards committee. This is the only method that'll work with everything, a transformer. So the AES has a number of standards committees to make some of this guesswork go away. And we realize that some manufacturers are literally don't know about existing standards and do things their own way. One example is there's a famous console maker that has effects returns that have an input impedance of 2K. Apparently they don't know that the IEC standard for unbalanced input impedances is 22K ohms minimum. And since consumer outputs are not designed to drive loads this low, the coupling caps are too small. Likely the low end response would suffer, as well as headroom and a number of other problems. So now we're at the question point. And thanks for your attention, by the way. Sorry about my voice.
Yeah, thank you so much. We've got a few questions in the chat. I don't know if anyone who wrote those questions wants to bring them up, or verbally now, or.
Yeah, I wrote one of those. This is John down in Dallas. You mentioned the 3-volt differential being a very dangerous level.
Oh, at an outlet, yes.
Yeah, between those two outlets that are in disparate locations. How do you measure that 3 volts? Do you
Well,
use
no, what
really
I was
long
talking,
meter leads?
no, what I was talking about there is the voltage at a given outlet. There should be 0 volts theoretically between the neutral prong and the ground prong.
Oh, okay. So it's not between outlets, it's at the outlet.
This is at the outlet. If you see
Gotcha.
3
Okay.
volts or more, that means there's a serious wiring error somewhere in the building.
Sure, sure. And is that how some of those little circuit testers operate with the little neon bulbs?
Actually, that's one of the shortcomings of the little lights. You can't find that kind of a problem with those testers. Because what they look at is the voltage on the hot side of the outlet with reference to the other 2 pins. And of course, if you follow those 2 pins, neutral and safety ground, they go back to the same place on the breaker panel. So there's going to be 120 volts with respect to either one of them. And you can't tell if they're swapped or not.
Wow. Well, I got to tell you, I feel like I sat here with Yoda. Thank you very much, Bill. I've never heard one of your talks and I truly appreciate it.
All right. I know it's some people used to accuse Dean Jensen of trying to get a drink out of a fire hydrant, but you know, there's just so much to cover.
Wonderful talk. Thank you.
Thank you.
Yeah, I wonder, I've got a few questions about way back in the beginning when you were talking about household wiring, right? So you talked about how ROMEX is actually really great. There's an older wiring, BX, and I can't remember if BX is twisted. So BX is 2 conductors inside a metal, flexible metal jacket, and I think that metal jacket is the earth ground.
Well, yeah, there's some, in fact, I was just reading that section of code the other day. There's some serious restrictions on using the flexible aluminum or steel in BX as a safety ground. Right. There's a length limit and there's the type of connectors that you bite into it with at both ends. It can be used, but it's in very limited situations. But yeah, to get back to the theory, it should have excellent properties in terms of ground induction.
Because I think they might be twisted right inside of that.
I would hope they are, yeah. But I haven't seen any in a long time.
Yeah, I must have owned an old, it was a 50s house, right? So it had a lot of BX in it. So does that mean if BX is twisted and ROMEX isn't, is BX better than ROMEX even?
Well, yeah, it depends on how accurate the twisting is. Right. I'd say they'd probably both be down in the lower part of that curve. It'd be an improvement over random wires, which is usually what you find in every commercial building. You know, the electricians just say, well, I need 3 circuits here. So 9 wires get pulled in and there you go. No controls at all.
Right. Right. So it's interesting then. It sounds like then, any of these ROMEX or BX are better than commercial wiring. So ironically, houses may be lower noise than commercial settings.
Yes. You probably have a much better chance of having a quiet system in a home theater than you would in a sound system in a commercial building.
That is ironic than in a recording studio, for example.
Well, yeah, but a recording studio, those are the people I'm trying to reach with pre-wire your studio before you move everything in. Twist, because it is nearly a miracle. It works really, really well. And you combine that with isolated grounding, and you can get yourself really well insulated. And in the studio, you could go even one step further and put in a distribution transformer and have a separately derived power where your ground reference now moves to your room. And it keeps the whole network very small and controlled. And you can get some extremely low noise systems that way. I'm doing a project for a manufacturer who doesn't want me to reveal their name, but everybody, it's a household word. They're building a new building and they want it to be as low noise as possible for testing purposes. So that's what we're doing there.
Excellent. Yeah, there's another question in the chat from James. What would you suggest saying to people who stubbornly argue for using the 2 to 3 prong cheater plugs to solve their ground loop problems?
Don't bet your life. Well, one thing that sometimes slows them down is that back when I wrote the paper in '94, I called a number of liability attorneys. There have been installation companies that have literally been sued out of business by the presence of an adapter. somebody got shocked. They didn't necessarily get killed, but they got a really bad shock. One case I learned about was a woman that got shocked, claimed her sex life was ruined and her sleep was interrupted. And, you know, it just wrecked her life since this shock. She sued for over $1 million and got it because the judge didn't give a rip that that adapter made the noise go away. The fact was you violated code when you installed it.
Right.
Those are,
And
that
the
installation
adapters
is-
say,
Okay.
the adapters either have a metal tab or a wire and says you must attach that to ground.
those adapters are actually intended to allow 3-prong gear to be plugged into an old 2-prong outlet, provided you connect the green wire or the tab to the screw that holds the cover plate on, which presumably connects to the BX, which goes back to the breaker panel and provides a safety ground. So they're intended to provide a safety ground, not to eliminate one. But nobody reads the fine print.
Yeah, it was quite difficult to convince this person. And again, like you
Sure.
said, I think you mentioned DJs. It's kind of funny. They were actually in a DJ Facebook group.
Oh, and they're a stubborn crowd too. I've had that argument several times.
I don't know if you can comment on more modern dimmers. I don't know. So incandescent dimmers were SCRs or triacs, right? And more
Right.
modern dimmers. I don't know. I actually don't know what a LED dimmer technology is inside, and if it's just as bad or worse or not as bad for hum these days.
Well, I don't have very much direct experience, but I know there are some new types. There are some that switch at higher frequencies, use MOSFETs, where and if the frequency is high enough, they can put enough filtering in the dimmer to actually keep the noise level way down. I think almost anything would be an improvement over the old SCR dimmers.
Well, some of them use PWM waveforms though,
Right,
which are very sharp on and off pulses.
right. Well, but if they're at 20 kilohertz, it doesn't take too much to slow them down. But
Yeah.
yeah, it can get really crazy out there, especially in lighting.
And I think there's a few more questions coming into the chat here. Phil asks, why is shielded cat cable better than UTP?
Mostly because it has the shield. Let me go back to that slide. It's easier to explain if I have a picture.
We'll have to share again,
Oh,
but that's okay. We can go back to the slide.
pardon, we got to learn how to run this.
So find the slide and we can do the share again.
It's right there. You see here that,
Oh, wait, let's share.
okay. Okay, can you see the diagram with the piece of purple coax?
Yep.
Well, pretend this is a shielded Cat5 cable. It means that every pair that's inside that shield will have the end-to-end ground voltage across the shield subtracted from all the pairs on the inside. So in terms of common mode voltage, the stress at the receiver is greatly reduced. Now the logical question is, well, how do I know if I have a common mode rejection problem in a Cat5 interface? Well, you might not if it's a digital signal. It'll just work and then all of a sudden it won't. Or somebody will flip a light switch and you'll get a big glitch or a dropout. But the common mode voltage ranges on digital interfaces are pretty small. Most of them are under a volt. If you take the pair and move it with respect to ground by a volt or two, the receiver is going to basically stop working. They're made for very tiny voltages. What saves them usually is the front end of a digital receiver for Cat5 has a high pass filter. So it rejects most of the power line frequency stuff. But the higher frequencies, like from an arcing contact or a dimmer, could still wreak havoc in a digital system. But if it's audio that you're using the pairs, if it's analog audio, it'll have the same benefit as shown here for the coax. It'll eliminate most of the common mode voltage in the cable at high frequencies. High noise frequencies, that is. Is that, I hope that's a good answer.
I think so. Phil's muted and isn't commenting.
Okay. Or you can write me, you know, if you've got it, if somebody has a detailed question that occurs to them later, my email is engineer_bill@verizon.net. I should have put that in the slides here, but I'm easy to find.
I wonder if I can ask. I wonder if I can ask just one more question. I think our sort of hard stop is in 12 minutes from now. But you know, many XLR cables exist, and they're the same size as RCA cables. I wonder why. Like, why haven't balanced cables caught on, at least in consumer audio goods?
Well, it's the connector. That's the expensive part. Now, just so happens, if there's somebody in the audience that can help, I have a patent that was granted about 8 years ago on a 3-contact RCA connector that makes all the appropriate bridging connections. So you can plug this 3-contact plug into an old output on, say, a CD player, and plug it into a new preamp that has a 3-contact input and have a balanced run all the way. It uses a sub ring on the shield. Deep in the inside, there's a 3rd contact ring. So it's downward compatible. So, and I'm looking for somebody to license it to, but so far, no luck.
So the center pin is
high.
Is like a 3.5 millimeter jack where it has contacts along the length of it.
No, there's no change to the center pin. It looks identical to an RCA plug.
Okay.
Except that on the inside of the shell, the outer contact, there's an insulated ring.
I see.
So if you put a corresponding ring on the balanced version of the RCA socket, they made up as a balanced interface. But if you plug the plug into a conventional one, it ties signal low and shield together, which is exactly the connection you want to make if you're coming from an unbalanced source.
Right. Cool.
Anyway.
Man, you take some incredible showers, Bill.
Inquiring minds want to know.
Yeah. Oh, may I ask a question about unbalanced outputs to balanced inputs? I've used the technique you've shown there for years successfully, but in the RAIN ubiquitous 110 note, they show the unbalanced output with a twisted shielded cable with the shield disconnected at the sending end. Do you see that as being useful? Yeah, no. With a twisted pair going to the RCA, pin to hot, shell to cold, and the shield lifted. That's how RAIN 110 shows that connection.
I'll have to look at that again, but I can't imagine any reason you'd want to disconnect the shield at either end.
Yeah, that's what I was thinking too, but I've seen that.
I mean, that's your hope for making the ground voltage difference between the two a little bit less, is tie them together with the shield.
Right.
And now extend your balanced input with a twisted pair all the way to the jack, so you don't see any of that ground voltage.
Right.
That's the idea. I don't know what they're thinking. I'll have to look at it again. But good question. Thank you.
Okay.
I don't know if there's any more questions here.
Could you go over slide 71 again? That went by really fast.
71.
Was it the one that had the license plate, Mr. CMRR?
That's really a circuit diagram thing.
71. Oh, it's the method that always works. Yeah, this is transformer isolation. Because the primary of the transformer floats, it doesn't care what the balanced output stage looks like, because the transformer has no ground reference. All that primary winding is looking for is a voltage difference between, well, in this case, the yellow and orange wire. That's a particular Jensen part there in the box, but so it doesn't matter. It could be grounded, it could be connected to an airplane and it wouldn't care.
So one thing I would add, if you remember that Wheatstone bridge that he showed, and he said that the worst case is when the resistors are all about equal. Well, what you're doing is you're taking one pair of those resistors and moving them into the megohm region
with the transformer.
So that other pair becomes insignificant in determining
rejection.
Yeah.
Thank you.
Does that make sense?
Yeah.
Yeah.
There he is. I was looking for you on the tiny screen here.
Yeah, sorry, bad lighting.
Yeah. Incognito mode.
Well,
Bill, if you ever need anybody to act as a testifier in relation to playing the role of a neutral wire, just call me. I was installing a transmitter one time up in Billings, and we had an old steel case drill motor, and I was holding on to the ceiling 3.5-inch transmission line, gonna punch a hole through a rafter and hit the button to operate the drill. And there was a wire that was broken off of the switch, the neutral, and I became the neutral.
Ooh,
And the breaker popped. And an interesting thing about that, we worked all night, but I never needed another cup of coffee.
I'll bet. Yeah. Yeah. I have a vaguely similar story. For 3 years, I lived and worked on a missile tracking ship in the Pacific, supporting all the Minuteman shots. It was a big ship with 3 huge radar dishes. There was no secret about what we were about. But I was working on a sonar transmitter, and someone I didn't know had disabled the high voltage safety interlock. So the ship is at sea and we're doing these 20-degree rolls. So just to stand up, and I'm trying to get a tube shield off of a tube in the back of the chassis in this, and there's a big door, metal door. So I open the door and I'm hanging onto the door with one hand, and I've got a pair of needle nose pliers. I'm going to reach in and grab this hot tube shield and pull it off. And my fingernail rubbed across the center tap of the output transformer, which had 4 kV on it. And it was still there. It was supposed to be dead. It arced a series of black holes through my fingernail into my fingers. And where it came out on the other side left a ring of blisters on my palm where I was holding onto the door. And I ended up flat on my back on the floor, gasping for breath after getting this huge 4 kV jolt from arm to arm. And all I remember is people standing over me saying, "Bill, are you okay?" And when I caught my breath, I said, "No, I'm not. I want to get the ass that disabled this thing and choke him to death." But yeah, bad shocks are very memorable.
Well, glad you made it through that one.
Me too.
All right. Well, I made it back, so that was good.
Oh, that is good.
Actually, just in time to close the meeting.
I know. Sorry.
Left here, I think. So I think we've got a hard stop coming up.
Yeah, I just wanted to remind you, yeah, we should wrap it up, but wanted to personally thank Bill for contributing here. Always valuable stuff. I'm going to have to go through the slides so in my off time and catch up on all that.
Are you going to distribute the slides? Because you have my permission if you want to.
Great. Okay. Yeah, we will. Yeah, we'll put a link to that. Kurt will put that up on the website and on the LinkedIn and Facebook sites. So
perfect.
It'll show up there.
Well, thank you guys for being a good audience.
Yeah, thank you so much.
What a great presentation.
Thanks, Bill.
Bill, all the best from Maria and me. It's Jim in Mississauga.
Oh, there you are. Yeah. How are you?
Great. Yeah. Great to hear you again, Bill.
It's good to see you.
All right, gents. Have a great evening. Thanks everybody for attending. Good to see everybody from out of town. And
Thanks for having the strangers.
all right, looking forward to the next meeting. And Bill, are you representing similar stuff related to SCE 0505 at some point? Or did that happen already?
I think it's scheduled for July.
July.
I'm going to do a maybe a little longer presentation and perhaps on a different specialty.
Yeah.
Yeah, this is this is a fraction of something I normally take about 4 hours to go through in detail.
Right. So that'll be upcoming, and that's on the published on the AES website as well.
Yeah, I think it's July 26th.
Cool. All right. Well, thanks again. Kevin, you are
everybody.
the host, and so you have to end it.
All right. All right. All right. Thank